Day 61 Notes, Advanced Algebra 2. Today we finish off the week with our discussions on polynomials, and this time we're looking at polynomial end behavior. And what that means is we're looking at what happens to the shapes of a polynomial graph as we go out towards infinity in our x direction, and when we go towards negative infinity in our x direction. What happens to the tails or the ends of each of these polynomial graphs? So the first thing that we're going to do is investigate graphs of even degree polynomials. So remember, when a polynomial is written in standard form, we have the term with the largest exponent listed first, and the exponent of the term with the largest exponent is known as the degree. In each of these cases, the degree is an even number. So let me switch over to the calculator and we'll talk about these three examples here. Okay, so here we go with that first function. We have f of x equals x squared minus 2. So when we're talking about end behavior, we're talking about the behavior of these functions as we race towards infinity in our x direction, both positive and negative infinity. So here the ends of the polynomial are facing upwards. As we go to the right, we approach a positive infinity, we go up in the graph, and as we go to the left, we also go up in the graph. Let's take a look at that next one. For this next function, we have f of x equals x to the fourth power plus 2x cubed minus x squared minus x plus 1. We again have the ends of the polynomial increasing towards infinity as we move to the right and to the left. So just like the first example, the ends of the polynomial are increasing as we move to the right or to the left. Let's take a look at that last example of an even degree polynomial. And here's that next example. 1/2 times x to the sixth power plus 5 times x to the fifth power. Well, this time as we move to the right, the polynomial does race off towards infinity, but if you're looking to the left here, it looks like it races towards a negative infinity. Now this doesn't follow the same pattern that we saw in those last two examples, but actually it does. We do have to be careful when we're graphing these polynomials so that we fit the entire polynomial into our window. Now if you see me moving this cursor over top of the graph, you might notice that over on the left-hand side, part of our graph is actually over here too. So if I choose the menu and zoom out, and pick that as my center point, you might be able to see that that graph looks like it drops down and then it comes back up. We can make this fit just a little bit better too if we choose Menu, Zoom, and Zoom Fit. Well, if we zoom out really, really far, that's what the graph has done here, you'll notice that it's approaching 4.41 times 10 to the 7th power. That's like having a 4 with 7 zeros behind it. That's 40 million. So the y-axis here actually increases up to 40 million. This is huge. This is very, very, very large scale. But I'm not too interested in the behavior of the function here towards the middle when we zoom out that far. Instead, I am worried about the polynomial's end behavior. And sure enough, if you look at the ends of this function, you can tell that it is racing off towards infinity in the y direction. It's moving up as we move to the right of the graph, and it also moves up as we move to the left of the graph. Now I'm going to take a few minutes here to reset this graph, and we're going to go back and look at the first two examples, something on a little bit smaller scale. Okay, here are those two functions again on the smaller scale. What I would like to do is investigate what happens if I change this leading coefficient. Instead of being a positive number, right now we have a positive 1 as our leading coefficient. Let's change that to a negative number and see what happens. So if I double click there and change that sign to a negative, take a look at what happens to the graph. It flips over. If we do the same for the other graph, change it from a positive sign to a negative, it too flips over. Now the change in this example is a little bit different. You'll notice that it's not exactly the same when we flip over. Here we have three pronounced curves to it, 1, 2, 3. But when I flip that over, let's try that again. You'll notice that the curves become less pronounced. So having the negative sign here does change the shape of the graph a little bit, but it doesn't change the end behavior. It's the same in either case. And in a moment, we're going to actually summarize our findings here. So keep in mind what's happening with these even degree polynomials. As long as the leading coefficient was positive, so I'm going to say leading coefficient greater than 0, then the ends of each of those polynomials seem to do this. They would race off towards infinity, or they would get larger as we moved to the right and to the left. So this is what the ends looked like. And if our leading coefficient was negative in these cases, then the ends of the graph seem to be going downwards. Let's take a look at what happens to odd degree polynomials. Here we have a polynomial x raised to the first power. That's an odd degree. This is x raised to the third power, and this is x raised to the fifth power. Each are odd degrees. Now in this first example, if we look at the end behavior of this polynomial, you'll notice that as we move to the right along our x-axis, we're moving up in function values along our y-axis. So again, as we're moving to the right, our function seems to move up. If we move to the left along our x-axis, then our function seems to go down. Now this is a linear function, it's a straight line, but it does have polynomial end behaviors. Again, moving to the right, the function goes up. We move to the left, the function goes down or decreases. Let's take a look at what happens if I raise this function or raise this variable to a power of 3, another odd degree. Here's an example of a function with an odd degree of 3. This time we see that we have two bends in the graph, but the end behavior is the same as what we saw before. As we move to the right along our x values, our function values seem to increase. So our function is going up as we move to the right. And the opposite's true as we move to the left. When we move to the left, the function value goes down, or the function decreases as we move to the left. Let's see if that holds true for our final example. And sure enough, this example holds true as well. As we move to the right, the function value increases, and as we move to the left, the function value decreases. So, in any of these cases, as long as, whoops, I've got a typo here, let me fix that. This is not meant to be to the fourth power. There we go. Let's see if that changes the look of this graph. Only slightly. But as we move to the right, we still increase, and as we move to the left, we still decrease. The end behavior of these polynomials are all the same. In each of these cases, as I move to the right in my x direction, my function values increase. They all go up and to the right. As far as moving to the left, we always decrease our function values. They go down and to the left. Now you'll notice that in each of these cases, the leading coefficient was positive and the exponent was odd. So what do you think might happen if the leading coefficient is negative in each of these cases? Let me try spreading these out and making that change so that we can check our guess. For whatever reason, it's not letting me change that. Let me pause the video and make these changes. And when I make those changes and I correct the leading coefficient and make it a negative number, you can see that on the purple graph and the green graph it's very obvious. As we move to the right, the function values decrease, and as we move to the left, the function values increase. However, changing the leading coefficient in that first example, or in that third example, it's kind of hard to see right now exactly what's going on in the end behavior. I think we get a pretty good guess of what's going on, but we should still adjust this window to make sure that it fits our data. So I'm going to choose Menu and switch to the Zoom option and choose Zoom option A, Zoom Fit. What that does is it allows us to zoom the equation out, and you'll notice that the x values stayed the same from -10 to +10, but our y values have now increased all the way up to 36,000 and decreased down to 36,000 as well. And here it makes it really clear and obvious that the movement of this orange function, as far as the end behavior goes, does follow the same pattern that we saw just a moment ago. As we increase our x value, the function decreases to the right, and it increases as we move to the left. So as we decrease our x value, the function then increases when our leading coefficient is negative. So let's switch over here back to our notes and summarize our findings. Essentially what we're saying is that for a positive leading coefficient, if we have an even degree polynomial, then the graph will open up. This is the example of a graph that opens up. The two ends will face upwards like that. If we have a positive leading coefficient and an odd degree, well, that means that the function will move up and go towards the right, and it will move down as we go towards the left. So the ends of the polynomial will look something like this. All of the movement on the inside can be anything that we can come up with, but right now what we're concerned with are the ends of each of these polynomials. And we can see that in this case, that's the direction that those ends will move in. When it comes to a negative leading coefficient and an even degree, the polynomial will open down. So those open downward like this when we had a negative leading coefficient and an even degree. And lastly, when we had a negative leading coefficient but an odd degree, that's where the function moved up towards the left and down towards the right. So the end of that function looked something like this. The ends of each of those functions looked something like that. Now the reason why we spend some time considering polynomial end behavior is that if we know how the ends of each polynomial behave and we know the degree within each polynomial, we could get a pretty good estimate as to what the graph will look like without having to use our calculator. Knowing the degree based on our conversation yesterday will tell us how many turns there can be in between the ends. And then if we were to take this a little bit farther and calculate the zeros of each function or the roots of each function, that will give us the exact number of turns that will occur in a particular graph. And it'll give us a pretty good idea of what a graph will look like before we even put it into the calculator. And especially for those of you that are students that are going to be moving on to higher level math, like pre-calculus and calculus, you'll need to know the design and layout of a particular function without the use of a calculator, because sometimes those upper level math classes don't allow that. So let's just take this as an example. Let's say that I have a function f of x is equal to x to the fifth plus 3x squared minus 2x plus 1. Now I just made that up. I have no idea what this is going to look like, but I do know that because of the leading coefficient being positive and the degree being odd, that the ends of the graph should look something like this. Okay, positive leading coefficient, which was 1, positive leading coefficient with an odd degree. I know the ends of the graph have to look something like this. Now, all of the movement on the inside can be whatever it needs to be. I know there are at most 4 turns, so I don't know, maybe this comes up here like this. There's 1 turn, here's 2, there could be 3, and 4. The graph could look something like that. It could be, it could be less pronounced from there. It might only have 1 or 2 turns. say one here and one here, or it could be very plain. I don't quite know. It could just do something like this, and that could still be an image that represents x to the 5th power. But I do know that it's going to look something like this, and if I were to take the time and find the zeros, let's say I was able to find the roots of this function, then I could know for sure exactly what this image might look like. If I know that this graph has to cross between those roots, then I'll have an even better picture of what the graph is. And here's an example of what that graph would look like after going to the graphing calculator. It does decrease as we move to the left, and it does increase as we move to the right. In this case, we had some slight bends here in the middle. It ran up and came back down, and then changed direction one last time and raced off towards infinity. So again, by just considering what the leading coefficient and the degree is, we could get a pretty good idea of what the shape might look like. And here was our guess from before, and there's the result from the graphing calculator. We'll continue practicing like this going into next week. Hopefully this is enough to make you comfortable and well prepared for tomorrow's Friday quiz.